Instructional design functions as an engineering discipline, bridging the gap between raw information and human comprehension. The designer is tasked with balancing a shifting set of situational demands against the unyielding biological realities of the human brain. We see this tension in the ADDIE model. These top-row variables, audience, content, and outcome, change with every project. But successful design requires mapping those variables against the vertical column on the right, the constants of memory, learning, and motivation. While delivery media, corporate goals, and academic environments frequently fluctuate, the biological mechanics of how human cognition processes data remain absolute. Effective design serves as the bridge between these unchangeable cognitive constants and the highly variable demands of a specific learning environment. A significant point of friction in the modern learning industry is the volume of competing frameworks, models, and acronyms. Cutting through this noise requires a distinction between theory and the frameworks built upon them. Theories describe how the brain processes information, while frameworks act as prescriptive models for organizing resources according to those theories. Many professionals treat these prescriptive frameworks as rigid templates without analyzing the underlying cognitive mechanics that make them work. By deconstructing these models, we can isolate the core structural logic used to organize resources for effective learning. We begin with cognitive theory, which views the human brain as an internal data processing mechanism. Gagne's 9 Events of Instruction is one of the most prominent frameworks within this category. This framework executes cognitive theory by breaking complex data into a strict sequence, moving the learner through 9 distinct learnable chunks. This sequential structure is optimal when teaching universal, objective principles to a novice audience. In a 6th grade classroom, Gagne's events can be used to systematically lead students through the strict rules of mathematical equations, ensuring each concept is encoded before moving to the next. When the content is rigid and the audience is new to the topic, the framework must provide a highly structured flow of information. The variables change in adult workplace training, where the primary goal is often the performance of a specific, measurable task. For these environments, Merrill's first principles provides a framework built around 4 instructional phases. Merrill's structure moves away from rigid steps and instead anchors all 4 phases around a single, real-world task or problem. When training employees on digital storyboarding, the designer skips abstract theory. They demonstrate the specific task and then move immediately to an application phase where the employee builds a storyboard. Task-centered frameworks succeed in corporate environments by aligning the learning process directly with immediate, measurable output. A third set of variables emerges when teaching subjective soft skills to adults, where there is rarely a single correct answer or procedure. This requires Kolb's experiential model, a framework designed for behavioral adaptation. Kolb relies on constructivist theory, the idea that adults learn best by actively constructing knowledge through their own concrete experiences and subsequent reflections. In sales training, this cycle might involve a role play with an irate customer, followed by a debrief where the trainee analyzes their performance and adjusts their behavior for the next attempt. Experiential frameworks are effective for complex behavioral change because they force learners to analyze their own mistakes within dynamic environments. On the surface, Gagne, Merrill, and Kolb appear to use entirely distinct terminologies and visual models. However, a designer must consider how to ensure learners actually progress through these demanding structures. This requires the engine for all frameworks: motivation, defined here by the value expectancy theory. Motivation is the product of 2 factors: valence, the value the learner places on the reward, and expectance, their belief that they can successfully complete the task. Because this is a product equation, if a designer fails to establish either perceived value or the confidence to succeed, motivation drops to 0. To understand the logic of these models, we have to look past their different labels and target audiences. When stacked horizontally, a common structural subtext begins to appear. We can identify a unified architecture hidden beneath these different terminologies. The first phase is pre-teaching. Gagne's attention gaining, Merrill's activation, and Kolb's experience all serve this same preparatory function. The second phase is teaching. Presenting the stimulus, demonstrating the task, or conceptualizing the principles are all methods for delivering and assimilating new data. The final phase is post-teaching. Assessing performance, assigning application, and active experimentation all test whether that data has been successfully accommodated. Despite their different psychological roots, these three prominent models reveal a shared tripartite architecture. This structural commonality provides a practical blueprint for day-to-day instructional design. Effective design avoids the blind application of rigid templates to every new corporate or academic problem. Instead, the process requires the same alignment seen in complex physical systems, where each component moves to meet a specific cognitive need. Understanding this architecture allows a designer to intuitively weave specific interventions based on their audience's variables without losing structural integrity. Mastering this field means anchoring unchangeable cognitive constants to a unified, adaptable blueprint.